John Chamberlain here with Fundamentals of Light and Laser. Today we're going to do Laboratory 1-6A, where we're going to measure the beam diameter and divergence from a laser. We have our helium neon laser all warmed up, sitting on a lab jack, and its beam is going to be cut by a knife blade that is sitting on a linear translator with a micrometer on it, so we'll be able to measure very fine adjustments to that blade position. The beam is going to be striking our photometer sensor here, and we're going to use that to measure the difference in power as we cut across the beam with the knife blade. We have our first position for our blade is exactly 15 centimeters from the output of the laser, and so we're ready to take our measurements. Since we're going to be using this micrometer to move our knife blade across the laser beam very precisely, it's important that we understand how to read this micrometer. Just to get our bearings, let's spend a few seconds and we'll see that 0 to 10 is the same as 0 to 10 millimeters. That's 1 centimeter and 10 millimeters. So each major division on the barrel is 1 millimeter. Let's crank it on down to exactly 1 millimeter and see what happens as we back out. So when everything is on 0, that would be 10.0 millimeters. This would be 10.10 millimeters, 10.20 millimeters, 10.30 millimeters, 10.40 millimeters, and now this would be 10.50 millimeters. And you'll notice on the barrel that we have passed one of the halfway marks between 10 and 11. So this is 1050, 10.60 millimeters, 1070, 10.80, 10.90, and now we are out to 11 millimeters, as we can now see the next major division after the 10 mark. We see the 11 mark. So this is 11 millimeters, and so on. So as we begin to back off in our readings, we'll be able to know how to transcribe these numbers. So I've positioned the camera so that you can see both of the micrometer indicating the position of the knife blade as it crosses the laser beam, and the photometer so that you can see the power readings. We've positioned the knife blade exactly 15 centimeters from the output of the laser, and so we're ready to start measuring. We're going to go the opposite direction the text suggests by moving the blade into the beam rather than out of the beam. So we are now at maximum power at 15.5 with the blade not blocking the beam at all. As I turn this around, I'll stop at 15.25 millimeters, no change. Now exactly at 15 millimeters. Now you see the beam beginning to drop at 14.75 millimeters. 14.5 millimeters. 14.25. 14.0. 13.75, 13.5, 13.25, and that looks like we're already blocked the beam entirely at 13.0. And this is the ambient light level that we'll subtract from all of the readings. So now let's move the blade further away from the beam and measure the beam diameter at that location. So here you see we have relocated the knife blade at 81 centimeters from the laser beam output, and We're measuring a maximum reading of about 0.782, and let's begin to move the knife blade into position until we begin to see a diminishing. Looks like we're already seeing it. There's 11.75 millimeters. There's 11.5 millimeters. $11.25 millimeters. $11.0 millimeters. $10.75 millimeters. $10.5 millimeters. $10.25 millimeters. $10.0 millimeters. $9.75 millimeters. $9.5 millimeters. $9.25 millimeters. $9.0 millimeters. $8.75 millimeters. $8.5 millimeters. $8.25 millimeters. $8.0 millimeters. And 7.75 millimeters, and it looks like we're pretty much have blocked the beam entirely at this point.
Rather than work with the data on the whiteboard today, let's use a spreadsheet. You'll see I have the data for the micrometer readings and the power readings for the knife blade positioned at 15 centimeters or 150 millimeters from the laser aperture. And over here we have the data for the knife blade positioned at 81 centimeters or 810 millimeters. Now for each set of measurements, let's create two more columns of data such that we will treat 13.0 millimeters for the first set of data as a zero position, and we'll subtract 9 microwatts from all of the power readings so that we'll treat the 9 microwatts as zero. And let's convert the power readings into a percent of maximum so that 766 microwatts minus 9 microwatts or 757 microwatts becomes the full power of the beam. So here I've added a couple of columns of data. You'll see I have the positions starting off at 0 millimeters showing 0% of the power all the way up to 2.25 millimeters showing 100% of the power. And the same thing for the 810 millimeter set of data. What we need to do is to find the distance between the 1 over e squared positions at each side of the beam. So that would be at the 13.5% power level and at the 86.5% level. To do that, we'll have to interpret our graph of data. Let's look at a graph of our data. Here's what the measurements look like, ranging from 0 to 100% for the knife blade positioned at the 15 centimeter point and the 81 centimeter point. And what we need to do is to interpolate the curve and find the value that would correspond to the 13.5% and the 86.5%. That will enable us to determine the beam width at 15 centimeters and the beam width at 81 centimeters. Now, there are several different measures of beam width that you can calculate. One of them is the 1 over e squared limits. You could also calculate the 10% and 90% limits, or the 20% and 80% limits using the knife edge. And if you have a beam profiler, a very sophisticated device that can actually measure the beam intensity across the beam, then you can come up with some even more sophisticated measures of beam width. For this lab, we're just going to use the knife edge, and we'll use the 1 over e squared points on either side of the beam. Now let's return back to the data. And as I said, we need to determine those 1 over e squared points. To do that, we will have to interpolate to determine what positions would in fact have yielded 13.5% if we had stopped and measured there. And you'll see that we've got measurements that in red here that encompass the 13.5%. And so somewhere between 0.7 millimeters and 1.0 millimeter positions will be that 13.5% power level. To do that, we're going to have to interpolate. To help you understand interpolation, I've prepared this little graph and some formulas here. If you'll have a relationship between x1, y1 and x2, y2, and we like to find the value of a point somewhere in between those 2 points, like capital X, capital Y, then we can set up a proportion and do some algebra and solve the equations for the unknown value of either x or y that we'd like. If you want to find the y value, you can see that we've just calculated the slope of the points and calculated the ratio of the distance between capital X and x of 1 and added to it y1 to find the new y value. Similarly, if we need to find the x value when we know the y. And in fact, this is our case where we want to find the x value that corresponds to a y value of 13.5%, which is in between our 2 known points. So now let's return to our data. You can see that I have entered the formulas to do that interpolation for the knife edge at 150 millimeters for both the 13.5% value and the 86.5% value. And subtracting those 2 measurement positions gives me the beam diameter at the 1 over e squared points of 0.64 millimeters. Similarly, I can do the same thing for the data for the 810 millimeter position, and you'll see that I get a beam diameter of 1.62 millimeters. Now, if I use the formula in equation 614 to calculate divergence, I get 1.48 milliradians as the divergence for our laser beam.
Well, that pretty much concludes the calculations for Laboratory 1-6A, where we've been able to determine the beam diameter and the beam divergence of a laser. You might want to try that again with a laser pointer or some other laser and just compare your results to see if all the lasers have the same divergence and the same diameter as the ones that we did in this lab. Good luck, and maybe we'll see you next time.